Hey, can you guys hear me okay?
Yeah.
Outstanding. So it's through the Bluetooth, through the mask, through the phone. It is kind of noisy in the lab, so I'm hoping that this was the best way to get audio to you guys while we're in here. All right, so we're out in the lab today. We're gonna do the machining part of the lab experiment where we're talking about the power and the chip thickness, and then you guys in your kit should have a bunch of different chips that you can measure. I'm going to demonstrate measuring the chips here, and then we're going to together design the experiment and have you tell me what data that you want to collect while we're out here doing this. So I think we're ready to go. Let's first thing, I'm gonna share the screen, and I'm gonna share the only screen this computer has, and I'm gonna make it free full size. All right, and so you guys should see that, and I'll move this over here so that you can see me while I talk. And turn on the autofocus so that I look pretty. Then I'm going to ask the people to stop using the power saw. Hey, hey, Ian. Thank you. All right, can you guys still hear me?
Yes. Yes.
All right, perfect. All right, so I think I'm sharing the screen. We've got this free file here for the machining of this part. So I'm just going to step through the simulation. And so the tool comes in, it faces off the front of the part. It actually moves over here close to the chuck, and it removes a little bit of material. And then it comes out to the front end and it removes a little bit of material. And the next operation is actually the operation that makes the surface finish that you got on the part. And so it comes in, it comes onto the part, it comes over, it comes off the part, and it moves the tool away. And so when I posted the code and brought it onto the machine tool, in between all of these steps, I have it stopping the machine and stopping the spindle so that it's possible to go in and retrieve the chip that was just made. And we'll watch that cut in just a minute. It'll do the next operation, and it'll do this operation. And so if we want to understand the surface finish on the part, what information do we have to collect from the program before we do the setup?
Feeds and speeds.
So specifically, what do we want to have? First off, do we actually care what the feeds and speeds were for the roughing operation and the facing operation?
No, but we care about what they are for the finishing operation.
We care about what they are for the finishing operation. Okay. So we'll look at the finishing operations when we do this. And so I had first is this, move you guys over here. Stop the simulation. So the first operation here is this facing operation, the contouring operation. The second operation is this roughing operation that made the part sort of the right shape. Now, honestly, the tool we're using could have removed all of this material in one pass. So I could suppress this roughing operation, and we could create the code, and it would make the same part, sort of. What would be different? What would be different about the part if I suppressed that roughing operation?
Would there be more deflection in it because there's a lot more cutting force with the finishing operation?
There would be more deflection part of the time, because the depth of cut, the average amount of chip that you're taking off would be much smaller here at the top than it is down here where it starts and where it finishes. And of course, as the radius gets smaller down here, you also end up with the fact that the radius is to the fourth power and the length is cubed for that deflection. Now, the deflection itself isn't really going to be a big problem for this experiment. But what happens when you have that kind of deflection is you often set up what we call chatter. And the part starts vibrating. And if the part finds a resonant frequency, it actually vibrates horribly, and it will damage the tools. It could damage the spindle in the machine tool if you do a lot of it. And it sounds bad. One of the things we tell you when you're in the lab making parts, running the machine tool, said if it doesn't sound right, go ahead and hit the emergency stop. If it sounds bad, stop the program, figure out what makes it sound bad. And people always ask, well, how do I know if it sounds bad? I said, you'll know. That's true for the most part. Now, sometimes because of the physics of our process, we have to put up with the bad sounds. But in general, when it sounds bad, if it's screaming or screeching, that means something's wrong. So anyway, I'm going to put that roughing operation back in. And so we have that roughing operation in there to keep it so that the depth of cut doesn't change drastically across the part. But if we want to know the surface roughness, then I think what we got to do is we've got to, what do we want to record from this operation? So if I open up that first operation, we see that it's, all right, so it's working on, here, I'll start with general. So it tells us we have a 55-degree diamond-shaped tool that we're using. And that's a tool that looks like this. Sort of. So it's in a tool holder that looks like this. The tool holder bolts into the turret of the lathe, and the cutting insert looks like this. And so that's the cutting inserts that we're using in the operation. That 55 degrees is the inside angle here at the tip. That's the 55 degrees. So we need to know, all right, we know what tool it is. What else do we need to know if we want to understand the surface finish?
The cutting radius.
We need to know the radius on the tip of the tool. right, and so the tool is, I'm going to write the part number for the tool. DNMG 15040H MS. That's the part number. And the manufacturer is Kennametal. All right, so if we want to know the radius on the tip of the tool, easiest way to do that is to Google it. Don't even have to spell it correctly. I don't want to buy a box of them on eBay. Oh, this website will probably have a good picture. All right. Corner radius is 0.08. What are the units there? Anybody know?
Radians?
The radius wouldn't have radians for units, no.
Oh, radius. Oh.
Would that be in centimeters because it's a UK company?
It's the UK version of the website I went to, so it was in millimeters, yeah, or millimeters, I think. So I'm going to go to the US website. And if you're looking for the cost of something, just to get a quick budget number, MSC Direct is a good place to go look it up. All right. And so each of these inserts is about 30 bucks. And corner radius is 1/32 of an inch. So R, little r, equals 1 divided by 32 inches, which is roughly equal to 0.8 millimeters. All right. What else do I have to know if I want to know the surface roughness?
Do you need the approach angle?
You don't need to know it, but for this tool holder, it's the side edge cutting angle, you mean?
Correct, yeah.
Yeah, it's 0 for this tool holder, but no, you don't need to know it.
You would need to know the peak to valley roughness.
Well, if we want to estimate the peak to valley roughness, what other factors from the program do we need to know?
The distance it travels per revolution.
The distance it travels per revolution. So the feed rate in the per revolution. So one of the things you see in the Spree, the CAM software, is that we can put in an RPM and it calculates the surface speed. And we can put in a per minute feed rate and it calculates the distance per revolution feed rate, or you can put it in the opposite. Whichever box you fill in here, it calculates the other one. And so for this operation, it was 0.015 inches per revolution. And actually, I went ahead and I labeled all of these. So the first operation is 0.015. Numlock 0.015. We'll do inches per rev just so we remember the units. And the next one was 0.005 inches per rev. And the last one was 0.010 inches per rev. All right, so we know the feed rates and the tool nose radius. Do we need to know anything else to calculate an estimated surface roughness? The quick answer is no. Okay. All right, so we've got that. And you guys have got your parts, right? You've got your parts at home in your kit. And so you felt the different roughnesses that made. Let's go ahead and watch this cut now. So I'm going to see if I can do this without unplugging everything. Somebody remind me to turn the screen share off before we get too far into this. All right, so I've got screen share, stop share. All right, so I've got the workpiece in here. We measured 3 1/4 inches from the face of the chuck. We already set the tool and the work offsets for this, and we've already run a test part successfully. So I'm not going to be too worried about that. Close the door. So I can focus a little bit here. All right, so you guys can see what's going on there at the tool, right?
Yep.
Correct.
All right, I'm going to go ahead and reset the emergency stops. And I'm going to go ahead and run the program. So it faces off the front of the part. And it does the roughing operation. And so what I have is I have it stopping in between each operation so that we could collect the chips that it makes during the previous operation. For this first operation, I don't actually want to collect any chips. But I do want to make sure that there's no chips built up on the edge of the tool. And so there was a little bit there. It was on the front of the tool. And I'm just going to make sure that there's no extraneous chips laying around in here from other people's stuff. All right. Or there's a little conveyor at the bottom of the lathe there that pulls the old chips out of the way for us. Let's see how well I can focus on this. All right, let's go ahead and run the next step. So what did you notice about that chip as it was being formed?
Big clump.
So here's the chip that it made in that pass. So it made a big ball of junk, basically. The other thing you'll notice, you can see it in this view, I think, here, is we do have that surface roughness that we talked about, but you can see there's a bunch of scratches on the part. Got the chip. Let's go ahead and run the next one.
That one seemed almost more stringy, if that makes sense.
It does. Do you remember which one of those had the higher feed rate?
The
First one.
first one.
The first one had a feed rate of what was it? 0.15 inches per revolution. Oh, you know what? Yeah, 0.15. That was the fastest feed rate of the feed rates we did. All right, and we'll do the last one. All right. And then the last thing it does is it comes in and it cuts the part off. And I'm using coolant on that cutoff operation. Otherwise, the part would get really hot. I didn't use coolant on the other operations because I wanted to be reaching in there and collecting the chips. And I honestly didn't want to get my hands all soggy every time I collected a chip. Dan, here's our workpiece. All right, so what do you notice about the workpiece here? Is it focused?
Cameras.
No, not at all. You can't see it. Let me just
super.
zoomy. There's our workpiece. And so do you notice the little nub on the end of the part there
Yes.
and not on that end? The autofocus back on. There, so you don't see it here. You do see it here. Why does that exist?
The PLAs explained this in lab. It was really interesting. It's just when it gets too close to the center, that little small spot can't support the weight anymore, so it just breaks off.
Right, it's actually not the weight so much as the cutting force. But yeah, the weight also. So the cutting force can be hundreds of pounds in this operation. And so it's that cutting force that eventually you just run out of the ability to withstand that force, and it breaks off. So every part that you cut off in the lathe is going to have some sort of a little nib like that. You can do things with the tool geometry to make those bigger or smaller. But whenever we cut off a part in the lathe, it's going to need a secondary operation to get rid of that little bit. All right, so with what we gathered from the program, and we can estimate the surface roughness on the part. What do we need to know if we're going to estimate the cutting force on the part?
We need to know the surface velocity.
We need to know, let me turn back on the screen share so you don't have unless you like looking at the back of my head. All right, screen share is on. Now you can see the side of my head instead of the back. You want to know the surface speed, okay? Now, we kept the surface speed the same for all of these operations. And it was 393 feet per minute. Now, why does it say 1,500 RPM?
Because the program did the math to convert from surface speed to RPM.
Did it ever spin 1,500 RPM while it was doing the cut? Maybe, but not continuously ever. So the 1,500 RPM is calculated based on the stock diameter of the workpiece as we defined it. So at 1 inch diameter, it would be spinning 1,500 RPM in order to be going 393 surface feet per minute. But we have it set to use constant surface speed, so we had it set to always do 393 feet per minute, regardless of the diameter. What's the problem when it gets to the center of the part if you tell it to always spin 393 regardless of the diameter?
So RPM would have to be really high.
Well, it'd have to be infinite at the very center of the part, right? And so the other thing we do is we set in the program, we set a maximum RPM. So I told it, no matter what the calculation tells you to do, never spin faster than 4,500 RPM, which is actually really fast for this lathe. The spindle is capable of 6,000 RPM. I'm not certain that the fixturing is capable of 6,000 RPM. All right, so, but we know the surface speed. We know the feed rate in inches per revolution. Do we need to know the diameters?
Of the cuts,
Yeah, or what do we need to know? Do we need to know the diameter?
we need to know the radius.
Is it important to know the feed rate as well?
Or, oh, yeah, no,
Well, we have the feed rates. We recorded the feed rates already here.
Okay.
I think we need to know the depth of cut. I told you the side edge cutting angle is 0. Is 0. I'll type 0. So how can we know what the depth of cut was? And it's not constant for the whole thing because we made this curvy shape on the part. That's okay. We're going to because we're making an estimate of the cutting force, we don't need to know exactly what the cutting force was. So if we look in here at our roughing operation, and remember the reason we did the roughing operation is so that we could have a constant depth of cut across the part. Go to strategy. Where'd it go? You get strategy. Then rough, sorry. Stock allowance was 0.050. So 50 thousandths of an inch was our nominal depth of cut because we kept our roughing pass 50 thousandths of an inch away from the workpiece. As an aside, if you're in the machine shop and it's in the United States, and you're talking to the machinist, and he tells you that the depth of cut was 50, the implied units are thousandths of an inch, and so the machinist would often write that as 50 and say it is 50, as opposed to 0.050 inches. It's part of the techno babble in machining. Do we need to know anything else? What else? What other data point do we need in order to estimate the cutting force?
I don't know if this is with the same way of doing it, but could you do it with the power that you're giving the thing and then like the efficiency that it's putting to the part?
We're going to come back at it in that direction, yeah.
Okay.
But if we want to estimate it first, how do we do it? What else do we need to know from the machinery's handbook equation to estimate power? Because if we know the power and we know the surface speed, we can estimate the cutting force, right?
We need.
Go ahead. I'm just going to focus. I'm going to
We
focus
need
on the
the
next
tool
thing we're
wear
going to need.
factor.
You're going to need a tool wear factor. Let's use a tool wear factor of equals 1. Wool wear. How about tool wear? All right. What else do you need to know?
We don't have K, right? So we need K.
Right. And so to find out what K is, what do you need to know?
The material that you're taking things off of.
Right. You need to know what the workpiece material is. So $60, $61, T6. Aluminium. All right, so we've got our workpiece material, and with that we can calculate what the power at the cut should be. If we know the efficiency of the machine tool, we could estimate how much of the power that went to the spindle got to the cutting edge. Or if we can now measure the power at the cutting edge, we could determine what the efficiency of the machine tool was, right?
Right.
So, all right. So let's see if we can measure the power during those cutting operations. I'm going to get another piece of stock ready here. So I pulled out another piece of stock. going to turn off screen share. And so can you see where it says spindle speed, spindle load?
Yes.
Yes.
All right, and it's not like backwards or anything?
No, it's not backwards.
Okay, because when I look at it on my Zoom screen, it's backwards, but I think they do that on purpose. All right, and I'll zoom in a little bit more. All right, so the numbers that we're interested in here is the spindle load. So here it says spindle load 0.0 or 0.0 kilowatts. I'm going to be busy watching the machine to make sure it's not crashing. So you guys are going to want to record this as it goes. To start with, let me go ahead. Actually, so before we do that, I'm just going to start the spindle spinning, and I want you to watch what it does. So what do you notice when it starts?
It jumps.
And then it settles down to some steady state that's around 0.4 right now, right?
Yeah.
So what that's telling us is that at this speed, it takes 0.4 kilowatts of energy just to make the spindle spin with this mass in the spindle and at this speed. And if we stop it, you see that it jumps again, right? So we're going to want to know what is the spindle load before it starts cutting and what is the spindle load when it's cutting. Actually, let's just use that 0.4 number, right? Because that's about the speed that we're going to be spinning when we do the cut. So remember that 0.4 number. I'm going to go ahead and run the beginning of the program. So practice watching that spindle load. Here's the facing operation. Here's the roughing operation. All right, so we're getting ready to run the first cut where the feed rate is 0.015 inches per revolution. You guys ready?
Yep.
What did we get for a spindle load?
At one point I saw a 5.6, it looked like, for the maximum.
What's anybody else have?
I saw 7, I think, for a quick second.
Anybody else?
Highest I saw was 5.6.
Okay. That 7 may have been when it was starting the spindle. All right, let's see
That's possible.
what we get for the let's see what we get for the next speed rate. All right, so I'm ready to go. Are you guys ready?
Yes.
And so now it's cutting. What did we get?
That one was around like 1 to 1.2.
1 to 1.2. All right.
And then it like jumped to like 4 or something. Then it was done.
Yeah, I'm certain that
3.9.
it jumped when the spindle
4.5.
when the brake was applied when it was stopping at the end there. All right, and let's do the last one. What'd you guys get for that one?
I saw a 5 at one point.
I saw
I got-
5.6.
I got a 3.8.
It was around like 3
I
and
saw
4.
a 6 something.
So, Professor, can I ask you a question?
Yep.
So, are we trying to look for the max or what we thought looked like the steady state?
What we really want is the steady state. I'm going to go ahead and run the cutoff operation, and then we'll do one more of these.
Surely can't you just have the computer find this for you rather than looking and guessing?
What would you have to do if you wanted to have the computer find it for you?
Take a video of it and go through frame by frame.
Graph
We
it.
could do that.
Set up a data logger.
So we could set up a data acquisition card and connect it directly to the power meter or to the to something that's measuring the current that goes to the spindle motor. And we've actually done that before with companies that were doing tool testing. We have one of our mini mills is fully instrumented to do that kind of data logging, measuring the power directly. And we used to have a lathe that was instrumented, but the data acquisition system that's connected to that lathe requires us to run Windows 98 or Windows ME in order to operate it, so we don't use that anymore. But I like the idea of going back through and looking at the video frame. Since we are recording this video, we go back through and get the data again. But I'm just run. I got another piece of stock set up, and I'm going to quickly run through this again. So we'll have two sets of data that we can compare. So right now it's about to do the facing operation.
And we're looking for the steady state, right?
The steady state during the cut, yeah. And since you guys can't see the cut and the monitor at the same time, I'll call out when I think it's about halfway through the cut. So now it's doing the roughing operation. All right, so I'm about to do the first feed, which is 0.15 inches per revolution. And now, and I'll do the second feed to 0.05 inches per revolution. And now it should be about steady state. And we'll do the final feed, which is 0.10 inches per revolution. Now it's steady state. On those fast ones, you have to be quick in deciding that it's the middle. Now I'm just going to go run the cutoff operation. All right. So I think if we go back through and look at the video file, we can pull out what the actual feeds were. We know what the depth of cut is. We know what the speed was. And so I think we have enough information now to write up about our experiment. Time is it? Oh, it's only about 5 minutes. Hey, James.
Yep.
Could you just very quickly go through the hand-in cam assignment?
Of course.
Okay. And somebody asked yesterday. Is now a good time, James, or should I try to go through it?
No, we can go through it.
Oh no, you got your screen sharing. Okay. James is going to explain what you're going to do for the CAM assignment that we're going to hand in for grading. And James is going to be coordinating all that grading. So if you have questions, you can directly ask him about it.
Yeah.
And there should be a link to it on Canvas now to the assignment page.
Was that there?
Where you can download this. I did it just before class started, so it should be there.
Okay.
If you go there and just hit refresh, it's there. But James is going to show you what we want you to do. Yep, cam to hand in. If you click that, just make sure the link works.
Ta-da.
Okay. All right, that opens the instructions. And somebody asked yesterday if there was a new CAM assignment for this week. And yes, there is. There was a typo in the assignment thing, so they were both labeled with the same chapter, but it was the correct link. It went to the correct information. It just was mislabeled on the link. But if you have done the CAM assignment for last week, chapters 4 and 5, you have enough information to do the CAM that gets handed in. This is going to be due next Friday, so the end of the week next week. We'll get you feedback on it if you made any mistakes or whatever, and you'll have a chance to resubmit this before the end of the term if you want to. So there is new material this week, but you don't need any of the new material to do this assignment.
No. So there's a starting file to download that's available. And we're going to look for you to face the part, create 2 pocketing operations, one for this oval pocket here, and then one for this like 3-layer pocket, and then chamfer the outside edge. So I've got one pulled up here as an example. And so things we're going to be looking for this are feed, speed, and depth of cut. It's possible to have different starting operations. You could create a pocketing operation to remove the initial material off the top instead of using the face mill. And for this example here, I used the face mill. Typically for a part like this, I personally would have used the end mill to remove the top, but it may be from the exercises you've gone through, it may be more straightforward to use the face mill here. You'll remove the top material, pocket out the oval pocket, and then pocket out the pocket with 3 layers. And there's a couple different ways you could do that, but as long as your part in the end looks like that, and you have the proper feed, speeds, and depth of cut, that's all we care about.
So go ahead, ask the question.
What do you mean by 3 layers?
There's 3 steps to it.
If you look at the part, there's 3 steps in that pocket, 3 different diameters.
Okay.
And you'll see that when you get the file. So the grading criteria is pretty simple. If you did something that is not exactly the way we would have done it, but it doesn't break anything and it makes the part, we mark it correct. If you do something that does not make the part, so if you leave material behind or you take away too much material, we'll take off some points for that. But if it doesn't break the machine, it's not catastrophic. But if you do something that would break the tool or break the machine, we take off more points. And so getting the feed, speed, depth of cut correct is a key thing. Making sure when you do your simulation that you have to hit stop, I think, James. Oh, collision detection. Make sure you have the collision detection turned on when you do this, so that it would simulate a crash if a crash is about to happen. And those are really the key things. If you can successfully make the cam for this part, you can successfully make the cam for most MQP parts.
How do we know the material of the tool bits?
The material is 6061 aluminum. I think we use is it the N1 or the N2 material group that we normally use?
N2 material group.
N2. So use the feeds and speeds for the N2 material group. And it's the standard tools that we have at the WPI shop.
Mm-hmm. So again, on our feeds and speeds page of our website, mfelabs.org. Also, if you ever do have the question of where a material falls in what group or in future projects, down at the bottom we have a material types link. And if you click on that link, it brings you to this page here, and this is going to break all your materials down based upon the group. So if you want to look, and you can go and find your aluminum 6061 that we're using in lab, you'll find that falls under the N2 group. Okay. And this is going to be an individual assignment. So each person's going to submit this. Yeah, and just double check when you open the file, make sure you're going to simulation parameters, and do make sure that the collision detection is set to full.
Professor?
Yeah.
Just one question about the work for this week. So it is the same link in both places, correct? Like for Monday and Tuesday and Wednesday and Thursday? We're just doing the one chapter?
Yeah. It's the same chapter. It's longer, a little bit more complicated.
Okay.
So yeah, it's supposed to be the same thing. It's just that when I put it up there, I labeled it chapter 5, and it's actually chapter 6.
Okay. So, but we're not doing the intro to 3-axis milling, or are we? Or
Yes, you are.
We are doing that?
That's the part that we're doing, is the 3-axis milling. And that should be what the link goes to. There's like 2 pages that reviews. So go to the assignment page, James. The Canvas page. No, not that. Here's the Canvas page. He's talking about today's.
On here, the one that we just went to, Cam and Hand-In, or on here?
Click on Getting Started with Cam, chapter 6.
Yeah.
So keep going forward. 6.1. Yeah. And there you go. So the page that's before that is just 1 page or 2 pages. So you want to do all of chapter 6.
No, I understand, but at the end there's 6 pages labeled chapter 6 3-axis machining, and it looks incomplete to me. I don't.
Yeah. No. It is what it's supposed to be. It's just supposed to be chapter. Yeah. So the chapter numbering is off. This should be like 6.3 or whatever, 6.2. But you do want to do those steps.
Will the quiz be posted at some point today?
Yeah, the quiz will be posted, and we'll go through it tomorrow at the beginning of lecture.
I have sent a message to the PLAs. They will have the Zoom meetings open for anyone who has questions during lab time. They will have the Zoom meeting open, available for CAM questions. Outside of the Zoom meetings, I suppose if we have questions, we could also start using the discussion board. I would ask that if you have a question and you're posting on the discussion board, go ahead and make sure you attach your file too, so that whoever would be the one to see the question could open your file and look for where you may be having your issue.
What time are the PLAs going on the Zoom at?
For right now, the normal lab session times.
So if you're on campus and you have questions about the CAM, just come a little bit earlier, prepare to stay a little bit late for your time, and just ask the PLAs in person, so they can open it up and help you. And if you're at home, somebody will be monitoring the Zoom channel, and just shout out and they'll answer you.
Toby, there's some question in the chat. So one student asked, will we be able to see our full quiz grade soon?
Yes.
And the other question is, do we still go to lab today?
Yes. If you're scheduled for lab today.
There's another question from Ethan. He says, when is this week's quiz going to be due?
The quiz is nominally due on Friday at midnight. Again, we're not enforcing the due dates and times. All right. If that's all, I'll go ahead and shut down.
Thank you.
Thank you.